Okay. Once again, good morning. How is everyone today?
Alive.
That's a good way to start. Excuse me as I embarrass myself trying to get the rope. I didn't fall that time. Okay. Waking up. There we go. Any questions, comments, concerns, etc. before we get started today?
Just that chapter 15 is due Tuesday, right?
Correct. Okay. So we've been talking about electric forces, and we did the example. We look at what the electric force would be between these two charged particles, these two electrons, and how things would be changed if one or both of them were protons instead. And someone actually sent in this picture to my email address. So that's staying in the slideshow from now on. I'd like to begin just with a cold open sample problem. So, this situation is a lot like the one where you would say as a kid, going like the plastic playground equipment. You go into like the tube that you climb through, and you would feel a static shock, or your hair, or maybe even under your clothing might try to move upwards towards the actual equipment itself. Or when you touch the Van de Graaff generator, the metal ball that gives up a charge, you touch it, your hair starts to drift apart. The electric force can drive objects to drift away from each other, and this tends to happen if the objects in question are charged with electrons and both have the same sign of charge. So these two objects here both have a mass of 15 grams, and they are charged with an amount of electrons such that they are both negative. Since they're both negative, they don't want to be anywhere near one another. And we are asked to try to find the charge on each of these two objects. And to simplify things, a little bit, I may not have made this clear in the wording on the slide, but both of these objects have the same charge. Whatever the number is, it's the same for both of them, and they are repelling each other evenly. The drawing is meant to show this. They're both pushing each other away at the same rate, so they both have the same mass, they're both at the same length of the string, and they're pushing each other away such that both strings are now at a 10-degree angle to the vertical. So we are looking for the charge on the sphere. This is going to be a multi-step process. I'm going to work it with you, but I just want to know what is the first thing you guys think we should look at to get a foothold in where we're going to go in order to find the Q's.
So the equation that FE equals
Okay, very good. So we have one formula so far that involves the electric force between these two objects and their charge. So looking at that is a very good place to start. This formula contains the charge of both objects, which is exactly what we want. So this is a very good starting point.
Could you say like 2Q? Since
Not 2Q,
wait, Q squared.
Q squared. the two q's are the same, so you're just multiplying q by q. So we can go ahead and tweak this just a tiny bit. Whatever the q is, they're both the same, so you can just rewrite it as q squared. This is, you can do this in general if the charges match each other in a situation. Looking at everything else in this formula, k is a freebie. We know what this number is. Want q, we're going to need r, and we're going to need some other way to find the force electric, or some other way to approximate it to then be able to plug it in.
Well, R is through like some kind of trig thing, because it's like, what is it, opposite? Could you use F equals to A? Because you're doing the math.
Very good. We start
What's
listing
your
some more
acceleration?
formulas.
I don't know, but you're giving the math, I mean.
We do have the mass. I'm listing all of the potential useful formulas that we talked about.
Yeah, so you would do opposite sine of 10, opposite over hypotenuse, yeah.
Okay, so, yes, this is sort of a combo question with principles from 1500. We're looking back at trig functions because you can never escape triangles. Sorry. In order to find the radius between these two objects, for simplicity's sake, we're just going to pick the radius from here to here, because that's what we can most easily figure out with the trig. And if we use this 10-degree angle, the drift horizontally is going to be the opposite leg. We also know the hypotenuse. So sine of 10 equals an opposite over hypotenuse. Make sure your calculator is in degrees mode. So what does that make the opposite leg of these triangles? Okay. Triangles are identical, just mirrored. Sorry, I'm just processing the fact that my calculator is not turning on. It means either the batteries are dead, which happens once every 3 years, or it means that Tiny don't work no more. Okay, Tiny lives. Let me just double check that answer. You repeat the number?
0.868.
Nice. The opposite leg is 0.868. We plugged in 5 centimeters, so that's going to be in centimeters. So, just tracking the distance from one object to the other, this piece here is that 0.868. This middle piece, we know from up here, is 3 centimeters. And then we have the opposite leg of the second triangle, which is the same as this leg. So what is the total distance between, what is the total radius we're going to use between these two spheres?
4.736.
Good. And that's in centimeters. What do we want it to be in? Yep.
0.04.
And that's our radius. So we can plug that in, no issues there. Now we just need another way to approximate the electric force.
Is this, like a wall and then it's hanging off of it?
These are hanging vertically from like the ceiling.
So you could say that A is gravity? right?
Well,
Or no?
these objects are hanging stationary.
I don't know.
They are not actively falling, they are not actively rotating, they are just levitating here. So we're looking at all of what would cause them to simply stay still like that. Like flashing back to 1500.
Like, isn't like gravity equal to the opposite thing? What is that called?
Okay, you're getting there,
I
yes.
can't remember.
It's okay. This is kind
Oh,
of
wait a second. I can't even find it. It's N. What does it stand for? I forgot.
normal.
Normal force, yeah.
So what's happening here is all the forces on both objects are balanced. So this is going to be a sum of the forces equals 0 type situation.
Wait, actually, I don't understand that because they're at an angle.
They are at an angle. So let's think about what all of the forces acting on these objects are.
So tension,
Tension points that way, because tension has to follow the road. Gravity pulls down. And if we're looking at this leftmost sphere, what direction is the electric force point in? Horizontal. Horizontal out this way. Well, all of these need to add up to 0, but none of them are nice and cleanly in the same axis as one another. So we got to do a little bit of trig and force addition to figure out what this is. Just a little bit. So I'm going to put this over here. Electric force is in the horizontal axis, so let's look at all of the forces in the horizontal axis. Some of the forces horizontally, we have the electric force, and that's going to point in the negative x direction, so I'm going to make that a negative number. Plus, what other piece here is in the x-axis?
It's probably T sine 10.
Yep, the x component of tension. So, kind of like what we did before, sine of 10 would be Tx over the hypotenuse. So the x component of the tension should be tension times sine of 10 degrees. And those need to add up to 0 because we are balanced in the horizontal axis.
Do they equal each other?
They do. So simplify this one line down. Fe equals T sine of 10 degrees. The trouble is we still have two unknowns. We want Fe, but we don't officially know what T is yet. So now we need to look at the vertical axis to help us figure that out. So some of the forces in the vertical axis, we've got gravity pointing down, so negative mg. Well, the g is negative, so that'll take care of itself. And what's pointing upwards is the vertical component of tension. So instead of T sine of 10 degrees, we're going to do cosine of 10 degrees equals opposite over hypotenuse. t cosine of 10 degrees, and these must add up to 0.
Because you could have drawn ty on the left side.
You mean put your vectors like
Yeah.
this?
Yeah.
You absolutely can. I did it this way because I was using the row capacity. Oh no. You can do it either way, however you prefer.
But the difference would be that the 10 degrees is the bottom angle.
Correct. So I tend to base my drawings on whatever's already in the picture as best I can. So, in general, we can use this vertical axis to figure out what t is, and plug the t back up here. For solving for t, that's going to give us mg equals negative t cosine 10.
Wait, why negative?
Because we have to subtract this to the other side.
Well, like, since g is negative, that already cancels out.
It will when we plug negative 9.8.
So I can't count mg as negative.
But you can. I'm going to go ahead and write negative 9.81 times m, and then it cancels. And said n is 15 grams, so t equals 9.81 times whatever 15 grams is in kilograms divided by cosine of 10.
So that was
1149.
Newtons.
Correct. This is a force, it's measured in newtons. So, our electric force will be equal to this times sine of 10. Is anyone having issues with the steps we've taken to get to this point? Because I've been mostly talking and pointing all day. Okay. So what does that give us for our overall electric force?
Point 0259.
Nice. And
That's
now,
Newtons?
it is newtons. Electric force is a force. It's a force caused by charged particles, but it's still a force, so we measure it in newtons. It has to be newtons so that it added together with all the other forces to create 0.
The unit of Q again?
Coulombs.
And then R is meters, and then K is,
K is newtons times meters squared divided by Coulomb squared.
okay, that's why it cancels out to get N. It has the Newtons.
On these constants, their units are always incredibly weird, and it's just so that everything cancels out evenly. But now we know everything we want to plug in everything except for Q. So Fe is 0.0259 equals K, which is always going to be 8.99 times 10 to the positive ninth times Q squared divided by R squared. Make sure you are only squaring that R. I might actually put that in parentheses. And when you work this through, you'll eventually get q squared equals something. You take the square root of both sides and you'll get q equals something. Notice though that technically speaking, it should be q equals plus or minus whatever that number is.
Yeah, you take the square root.
Correct. That's because in this situation, if the charges have the same magnitude, this situation would only come about if they also have the same sign. But you could do that if these were both negative or both positive. So the plus minus on the answer makes sense here for that reason. They're either both negative answer or they're both positive answer and the same number.
Wait, they're either both positive or both negative because they're going away from each other?
Correct.
I got 8.035 times 10 to the negative.
Boom. I wrote on top of it, but there it is. Does anyone disagree with this number?
Coulomb.
Yes. We solved for charge, so the unit is coulombs.
Wait, so we have to write the positive negative? You can't choose one?
Technically, the problem never told us if these were positively charged or negatively charged. So the most accurate thing to do would be to write the positive or positive negative. Because again, if they're both negative 8.05 instead of negative 8, this works. If they're both positive 8.05 instead of negative 8, then this works. We didn't specify either way, so this is the most accurate thing to say. Any questions about this example? Okay. So, you've looked at this formula a little bit now, used it a few times. I'm going to switch it back to its normal form now. We used this a few times, and this formula is the math behind where electric force comes from, and that electric force is the driving factor behind pretty much every electrical thing on Earth. Electrical current moves because there's electric force pushing the electrons through the wire. Lightning happens because the electric force pulls the electrons out of the sky, so on and so forth. But I don't think I commented on this yesterday yet. Does this formula remind you of something else? The way that it functions, the general way, shape that it's written in, the variables present. Does it resemble something else you've seen before?
Like this here?
Within Physics1500. Within Physics1500. I almost said 15,600.
Oh my God.
No? Continue the thought.
Well, it's probably not right. I was gonna say force of gravity formula.
Humans are real good at pattern recognition. You're absolutely right. These two things look very suspiciously familiar to one another. And that's on purpose. So, the electric force depends on some constant the magnitude of the two things creating the electric force and how far apart they are. The gravitational force depends on some constant, the magnitude of the two things creating the gravitational force and how far apart they are. These are similar because they're similar. The two forces involved here are literally cousins. In upper level physics, we have this collection of forces that we say are the four fundamental forces that hold the entire universe together. They are all very similar in how they behave. They're all literally relative to one another. And they're the four things that, again, at the core of the universe are literally holding atoms and planets together to allow things to continue to operate smoothly. Those four forces are the strong nuclear interaction, the weak nuclear interaction, gravity, and the electromagnetic forces, plural. So gravity and the electromagnetic forces are, again, literally cousins. They behave similarly because they're just kind of variations of the same thing. And the electric force is not the only member of this little branch, because electricity and magnetism are technically different but related things. But even if electricity is just one branch of this of the family tree, that branch is still cousins of gravity. And what gravity does is, whenever you have two objects with mass, everything with mass is perpetually exuding a gravitational field. Did the term gravitational field come up in your previous class? Okay. I'm going to just move ahead now. So in physics, this is not anything you're going to need for this class. I'm just sort of showing where the logic train comes from. This is not something you're going to need on your formula sheet. This is just showing the math for gravitational fields so that we can then compare it to the math for electrical field. Gravitational fields are created by any particle that has mass. This includes single particles, this includes planets. If something has mass, it is literally bending space-time around it by creating this gravitational field. Everything with mass does this. And when two particles are near each other and their fields overlap, that's where the gravitational force comes from. So all objects that have mass are creating this field, and when fields interact, a force happens. So right now, your gravitational field is overlapped with the Earth's gravitational field, and those overlapped forces pull on each other.
With the Earth being stronger, which is why we're not blue.
The Earth has more mass. So it has a more powerful gravitational field. The force that the Earth exerts on you is the same as the force you exert on Earth. So if I weigh 1,000 newtons, I'm also pulling on the Earth with 1,000 newtons, based on this formula here. The thing is, the Earth's mass is so huge that force is not going to make it budge.
Is there something that would?
The sun. Maybe the moon to a lesser extent. The moon affects us a tiny bit. It more noticeably affects the ocean and the planet itself. But you need to be on the scale of planets to move planets. No amount of one human jumping up and down is going to have any significant effect. So, gravitational fields overlap and forces happen. It's exactly the same with electricity. I'm going to swap these from M1 and M2 to Q1 and Q2. Particles with mass give off a gravitational field. When those fields overlap, forces happen. Objects with charge give off electrical fields. When those fields overlap, forces happen. So gravitationally speaking, a field depends on the mass of the thing creating the field and how far apart from it you are. On planet Earth, we're pretty close to Earth, so the field here is very strong. The further away from Earth you get, the weaker the Earth's field is on your location. So when you examine an object's field, you're basically just examining the effect that that object has by itself. Notice this formula for gravitational field only has one mass in it. This is just what the Earth is doing alone at that point. You're examining the Earth's effect at a radius from Earth. The same can be done with electricity. You will want this formula. All particles with charge are exerting an E field in all directions. The most fundamental, I almost said fundamentary, most fundamental things that possess charge are our girlfriend's proton and electron.
Wait, are exerting a what?
One more time.
You said all particles with charge are exerting
Electric field.
in all
Everything.
directions?
In all directions. Earth exerts a gravitational field in all directions. Charged particles exert an electric field in all directions. So we tend to draw positive particles exerting field outwards. The one proton is exerting a field in all directions. So it doesn't matter what side of it you're on. The field strength in any region of space, doesn't matter where you put, doesn't matter what region of space you're looking at, the field strength is going to depend on the charge creating the field and how far away from it you are. Doesn't matter left, right, up, down, just distance from. Notice, I drew these arrows like this for a reason. When you're very close to the proton, there's a very high concentration of field arrows. The further away from the proton you get, the less concentrated the arrows are. The weaker the field is, the farther away you get, which is why the farther away two things are, the weaker the electric force, the weaker the gravity. So we could say, put a little finger stick right here, measure how far from the proton we are, figure out the proton's electric field right here. We could also extend our yardstick and figure out its field strength right there. As long as you know the strength of the charge creating the field and how far away from it you are, you know the strength of the field at that spot. The field strength will change depending on how far apart from the particle you are. So this, you don't need necessarily all of this. This is just how this math was created. What you will care about are these. This has just simplified the previous slide down by a couple of steps. So capital E, underline, is electric force. This is the variable for electric force. And that is going to be measured in newtons per Coulomb. The primary formula for electric field is K times the Q of the charge creating the field divided by distance from the field, or the distance from the charge. But you can also test an electric field by putting a test charge within the field and seeing the force that charge exerts on that particle. So this proton's exerting an electric field. If we wanted to test that field, we could just drop an electron right here and see what happens. Drop down this electron. This is going to be our test charge. So Q test. This particle is in the electric field of the proton, since the proton is exerting it infinitely in all directions. Only function is just how far away from it you are. We drop this electron near it, and we watch it. We measure the force that the field is going to exert on it, and that force divided by the charge of the electron can also tell us the field strength in this spot, just where we drop the electron. As soon as the electron moves, it's in a new spot. There'll be a new force based on the field strength in that location. E fields are kind of hard to conceptualize because we literally cannot see them. So I know I've been saying a lot of words and pointing. How do you guys feel?
Wait, so why can you get rid of the charge of the test and move it into just the radius? Like, why does that not matter and just the radius matters?
Say again, sorry.
Like, why does the charge of the test charge not matter and the radius does matter?
Well, there's two ways to calculate electric field. And let's consider them two separate methods for right now. First method. You know the charge of the source particle, and you know how far away from it you are. If you know those two things, you can use this piece. Second method. So first method is E equals KQ over R squared. Second method, E equals force divided by Q. This method entails, say for example, you didn't know the charge of this object. You knew this is giving off an electric field, but you didn't know what kind. We don't know it's a proton, we don't know sign, we don't know magnitude, anything like that. If you didn't know what that was, or even how far away from it you were, then you can use E equals F over Q. You know there's an electric field, so you're going to drop a test charge in that electric field, and then you let go of it and measure the force that the field exerts on the particle.
Is that FQ?
Correct.
And then how would you get E?
So in this situation, if you drop an electron into the field, and the field exerts this force on the electron, that force divided by the strength, the charge of the electron, is equal to the E field.
So you have to be given two of the three. You can't like solve for like the electric field another way to put it into this formula, or solve for the force another way and put it into this formula.
You will be given everything you need to be able to use one of the two iterations of this formula. I promise you that. These are just the two primary methods for determining field strength. And just to have in your notes, E fields exert force on charged objects. So if this is our test charge, the field will exert a force on it. That force divided by the magnitude of the charge is equal to the E field strength in this spot. I want you to notice though, if we ignore this part real quick, we're ignoring the electric field part. We're just looking at force on charge divided by charge equals KQ over R squared. Does that look familiar? I asked that twice today. F over Q equals KQ over R squared. This piece is only one step away from this. This form is of the form where you are simply solving for the force between two particles. This form, you're examining the field that one particle gives off as it affects the other one. Because the field is the reason this force exists. It's all connected.
How do you choose which one's the text and which one's the source?
Ultimately, it doesn't matter. Because depending on how you do the algebra, if you multiplied this over, you could divide Q source and put it there instead. So the answer will be the same as long as you're looking at the same two charges affecting each other. We're nearing the end of the period. I don't want to hold you today, so I'm just going to give you a couple more things to digest, and we'll do some examples next time. E fields are technically vectors because they're pointing outwards or possibly inwards in all directions. They point in the direction of the positive charge. Sorry. The way I describe things verbally is different to the way I describe things in the notes. Let me say it like this. E fields are vectors because they do point somewhere. But the vector is really, does it point outward or inward? I drew this proton exerting field outward from itself. The thing that makes electric fields different from gravitational fields is that for gravity, you can only have positive mass. You either have mass or you don't, which means gravitational fields, gravitational forces only pull inwards. E fields, though, you can either have no charge, positive charge, or negative charge. So E fields can point out or in. Negatives, we tend to draw E fields going into a negative charge. They draw the field into themselves. And the fact that you have two different signs of charge is why electric force can point either in or out. Rather than with gravity where there's just one combination, positive mass, pull in. You can either have positive, positive, negative, positive, negative, negative. Yes?
So you know how in the lab, like when you would put them next to each other, it would move like the arrows of the one beside it?
Mm-hmm.
So does that mean that the other charge is creating a force that moves the electric field of the other object, like that?
I wouldn't use those words, but you're getting to the correct concept. The fields of two particles, like when gravitational fields overlap, that's where gravitational force comes from. When E fields overlap, that's where the electric force comes from. Because this test charge has its own E field, and that field interacting with the first charge is why there's a force. When the fields interact, then the fields are going to bend. In this particular case, going positive to negative, the field is going to bend from positive to the negative. Fields always want to go from plus to minus. And this bending is what creates inward force. If we had a positive next to a positive, though, the lines are going to bend away from each other because they don't want to do that. Positive does not want to go to positive, so the lines are going to butt up against each other and push away, which is why those repel. Same with negative and negative. And I don't want to hold you too much. So to give it a visual for that, this is a very convoluted representation of an electric field. I had to go through a lot of steps to get this particular illustration. Basically, the actual lines are iron shavings floating in oil that have been electrified. The shavings are lining up based on the E field. This is just what one particle looks like by itself. This is what happens when you have a positive next to a negative. Positive is sending E field out. That field is going to bend and go towards the negative. That bending, the fact that we are bent and are now going from positive to negative, is what creates the attracting force. Yes?
How do I know which is positive and which is negative?
From this picture, you don't, strictly speaking. But this type of nice even bending from one to the other is what tells us they are at least opposite charges. So on the other hand, if they're the same charge, we get this. They bend away from each other, they don't want to overlap, and that creates the repelling force. You'll get this positive, positive, or negative, negative. I've talked a lot, I've held you up a little bit, I'm sorry. Do have a wonderful day. Do be pondering this, because tomorrow we're going to pick up with a little bit of E-field math to end the chapter. Let me know if you have any questions. Do have a wonderful day. Be working on your assignments, do your lab this week, yada yada, all that good stuff. Yeah, stay warm.